Welcome to lecture series on digital electronics under EPG Pathshala. In this module, you will learn about multiplexing and demultiplexing. Multiplexers and demultiplexers are basically used for sharing the resources. There are many applications in day-to-day life wherein we use multiplexers and demultiplexer. Let us take an example of cable TV. In cable TV, the signal that we receive from satellites or from cable is collected at one set-top box and then it is given to your TV channel. In addition to that, when we talk about computer networking, the resource like printer, hard disk can be shared amongst the many computers. In addition to that, if you look at the day-to-day application like the telephone network, almost all telephone networks they make use of multiplexers and demultiplexers. In smart PC based instrumentation, we use analog to digital converters, and this analog to digital converter is capable of collecting the information from multiple sensors. That requires some kind of multiplexing in acquiring the data. In this module, we will focus it on the basic principles of multiplexing and demultiplexing. We will talk about the architecture, we will talk about the truth table, logic diagram and applications of multiplexers and demultiplexers. In this module, you will explore everything about multiplexers and demultiplexers. Initially, you will get familiar with the principles of multiplexing and demultiplexing. Multiplexers are used for sharing the resources. The logic symbols, logic diagram and truth tables of the multiplexers will be studied. In addition, you will understand the concept of demultiplexer along with symbol, logic diagram and truth table. How multiplexers and demultiplexers can be used in variety of applications will also be explored. Let us now begin with principles of multiplexing and demultiplexing. Let us consider a system with n inputs. Multiplexing means sharing. It means many to one. A multiplexer is a device that allows digital information from several inputs to be routed onto a single line for transmission. The multiplexed data is transmitted over a single line to a common destination. Demultiplexer accepts this data and redistributes it to the n outputs. Note that for simplicity, the additional select inputs are not shown here. Data select lines are used in many into one operation of a multiplexer and one to many operation of demultiplexer. In short, multiplexers and demultiplexers are combinational circuits designed to provide sharing of resources. The keyword is sharing. After learning the basic principles of sharing, let us now talk about architecture of multiplexer. Multiplexer means many to one. Multiplexer is a combinational circuit which is often used when the information from many sources must be transmitted over long distance and it is less expensive to multiplex data onto a single wire for transmission. Multiplexer can be considered as multi-position or rotary switch. There are n inputs and one output. The switch position is controlled by the selector lines. The select inputs decide which input is connected to the output. A multiplexer can be considered as semiconductor equivalent of multi-position switch. It is a combination logic circuit which has many input lines and a single output line. The basic operation is controlled by a selector lines that routes one of many input signals to the output. Multiplexer are also called as data selector or a router because it accepts several data inputs and allows only one of them to get through to the output at a time. Let us now understand the relationship between inputs and outputs of a multiplexer. The basic multiplexer has n input lines and single output line. It also has m select lines. The relation between number of select lines and number of data inputs are 2 raised to m is equal to n. This is an important relation in multiplexer. Using basic relation between the select lines and number of inputs, we can classify multiplexer into different types. Let us consider 4 simple examples of multiplexer. When the number of select lines are related with the base of 2, let us consider 2 to 1, 4 to 1, 8 to 1 and 16 to 1 multiplexers one by one. Now, in 2 to 1 multiplexer, the number of select lines are to be considered as a single one, whereas the data inputs are 2, the output is 1. The data inputs are D0 and D1 and the select line is represented as S0. Whereas, in case of 4 to 1 multiplexer, to accept 4 data inputs, namely D0, D1, D2 and D3, the number of select lines required are 2. These select lines are S0 and S1. Now, in this case we are considering S1 as MSB and S0 as LSB. The select lines will route the proper data from input to the output. Let us now consider the case of 8 to 1 multiplexer. Here the number of input lines are 8, whereas the select lines required from the basic relation are at least 3. The data inputs are labeled as D0, D1, D2 up to D7, whereas the select lines are labeled as S2, S1 and S0. These are the 3 select lines that are required, assuming S0 is MSB. These 3 select lines can select any one of the input to the output, whereas in case of last multiplexer, which is 16 to 1 multiplexer, we have 16 possible data inputs and those could be selected by 4 select lines. These select lines are labeled as S3, S2, S1 and S0. These 4 select lines can select 1 out of 16 inputs to the output, and in this way we can see multiplexer can be used as intelligent switch. The selection is done by the select lines. Let us now discuss the design of 2 to 1 multiplexer. Let us consider D0 and D1 as the data inputs, S0 as the select line and Y as the output of the multiplexer. In the function table, we consider select line S0 as the select input and Y as the output. When S0 is 0, the output receives the data D0, and when S0 is 1, the output Y receives the data D1. Let us now prepare a detailed truth table for 2 to 1 multiplexer. In this truth table, S0, D1, D0 are the data inputs and Y is the output. Please note that D1 is MSB and D0 is LSB of the data. For S0 is equal to 0, we have 4 possible combinations for the inputs 0 0, 0 1, 1 0 and 1 1. It is observed that Y always follows D0. For S0 is equal to 1, we have similar 4 possible combinations for the inputs. It is observed that in this case Y follows D1. Once the logic symbol and function table as well as truth table is ready, now the next step is to prepare K-map for designing the logic circuit. In this example, we need to prepare a K-map of 3 variables. Let us consider 2 rows for S0 and 4 columns for the data D1, D0. Once the K-map is prepared, the next obvious step is to map the truth table into the K-map. Write 1s in the cell where the output is 1. In this K-map, we have written 1 in 4 cells as shown here. For example, using K-map, let us now identify neighboring cells and form the groups or pairs. In this example, it is observed that there are 2 groups possible. From the first pair, we can eliminate D1 as it is changing in the pair. Thus, this pair contributes to S0 bar D0 in the output. Similarly, in the second group, D0 gets eliminated as it is changing in the pair. Therefore, we get S0 and D1 as the second term in the Boolean expression. The final Boolean expression is the sum of 2 product terms as shown here. This indicates that either D0 or D1 will appear at the output decided by the value of S0. The logic circuit can be implemented using 2 AND gates and 1 OR gate. The NOT gate provides complemented and uncomplemented form of select line S0. The interconnections are made to AND gate to provide the necessary product term. Let us consider simple interconnections in this diagram. The first AND gate has 2 input, one of them is from S0 bar and the second is D0, whereas second AND gate receives directly uncomplemented select line, that is S0 and D1. The output of both AND gates are given to OR gate to provide sum of product terms. The second type of multiplexer is 4 to 1 multiplexer. The logic symbol indicates there are 4 data inputs, namely D0, D1, D2 and D3 and single output Y. For 4 data inputs, we need 2 select lines, namely S1 and S0. While preparing the function table, we write S1 as MSB and S0 as LSB. The 2 select inputs provide 4 input combinations for selecting the proper data input at the output. The output Y receives D0 when S1 and S0 both are at 0 input. Similarly, output Y receives D1 when both select lines are receiving the input 0 1. Output Y receives D2 when S1 and S0 is equal to 1 0, whereas the output Y receives D3 only when both the inputs are 1 1. So, select lines can decide whether D0, D1, D2 or D3 should appear at the output. That is why we are calling multiplexer as intelligent switch. From the function table, we can directly write the Boolean expression in sum of product form. Each row of the function table provides the product term and the Boolean expression is Y is equal to S1 bar S0 bar D0 ORed with S1 bar S0 D1 OR with S1 S0 bar D2, OR with S1 S0 D3. This is the Boolean expression for 4 to 1 multiplexer. Based on this Boolean expression, we can draw the logic circuit consisting of one OR gate with 4 inputs. Each product term is represented by 3 input AND gate. One of the input to the AND gate is the respective data input. The select lines S1 and S0 along with the inverter provide the select input either in uncomplemented or complemented form. We will make the connections to the AND gate as per the requirement of the product term. For example, the first AND gate receives D0 as data input, S1 bar and S0 bar as inputs. Similarly, rest of the AND gates receives the appropriate inputs as per the product term. So far we have discussed the construction of simple multiplexers using discrete logic gates. It is also possible to extend the same concept for 8 to 1 multiplexer as well as 16 to 1 multiplexer. Commercially, multiplexers are available in MSI IC form. The table indicates multiplexer IC numbers for TTL logic family. Let us now talk about these commercially available ICs. IC 74150, it is a 16 to 1 multiplexer and the output of this multiplexer is inverted input. IC 74151 is 8 to 1 multiplexer in a single chip, which provides complementary outputs. IC 74152 is 8 to 1 multiplexer wherein the outputs are inverted inputs. IC 7153 contains 2 multiplexers, dual 4 to 1 multiplexer. The output is in the same format as input. So, if it is uncomplemented, the output will be uncomplemented. IC 74157 contains quad, that is 4 2 to 1 multiplexer in a single chip and the outputs are same as input. Whereas, IC 74158 is quad 2 to 1 multiplexer, the only change is the outputs are inverted inputs. In addition to TTL multiplexers, we have CMOS multiplexer ICs which are more popular amongst the digital system designer because of low power consumption and flexibility. Let us discuss about these multiplexer ICs. These multiplexer ICs are in the family of 40XX. Let us consider the IC 4051. It is 8 channel analog as well as digital multiplexer or demultiplexer. The same IC can be used as multiplexer as well as demultiplexer. There are 8 inputs, you can generate one output. So, it provides 8 to 1 multiplexer or it can act like 1 to 8 demultiplexer. The additional feature of this IC is that it not only allows you to pass the digital data, but can be used even for multiplexing the analog signal. That is why CMOS multiplexer ICs are more popular as compared to TTL ICs. IC 4052 is a dual 4 channel analog multiplexer slash demultiplexer. Even though we are writing analog, that does not mean digital cannot be passed. any signal, whether it is analog or digital, will be routed to the output. IC 4053 is triple 2 channel analog multiplexer or demultiplexer, whereas 4067 IC can be configured as 16 channel mux or demux. Similarly, 4097 has a speciality that it accepts 8 channel inputs, but those could be differential inputs, and it can be configured as multiplexer as well as demultiplexer. In many situations, an enable or getting input is added to the multiplexer. The multiplexer will be enabled or operative only when the enable input is active. In this case, enable is active high. When E is equal to 0, the multiplexer function is disabled. To enable multiplexer, E must be set to 1. You can see this through the function table of 4-to-1 multiplexer as shown here. Depending upon the select input combinations 0 0, 0 1, 1 0 or 1 1, the output of the multiplexer could be D0, D1, D2 and D3 with the assumption that the enable input is 1. As number of inputs to the multiplexers are limited, say up to 16. To meet the larger input needs of multiplexer, smaller multiplexers can be cascaded together for further expansion. This method is also known as tree multiplexing. Higher order multiplexer can be constructed by using lower order multiplexers. Let us now consider the construction of 4-to-1 multiplexer using 2-to-1 multiplexers. To obtain 4-to-1 multiplexer, we will use 2-to-1 multiplexer at level 0, where each multiplexer will accept 2 inputs with a select line S0. So, for first level multiplexers, both the multiplexers will require a single select line, that is S0. The data inputs received by the first multiplexer are D0, D1, whereas D2 and D3 are connected to the second multiplexer. The output of these two multiplexers are further connected to the next level multiplexer, 2-to-1 multiplexer. The only difference is, in place of connecting S0 to the second level multiplexer, the MSB, that is S1, is connected to the second level multiplexer. So, S1 will decide whether the first multiplexer or second multiplexer output is to be transmitted at the output. So, if you look at the function table of this multiplexer, you will find that when S1 is 0, naturally the first multiplexer data D0 or D1 will appear at the final output, and when S1 is 1, the D2 or D3 will appear at the output. So, this is the way we can cascade the multiplexer. The principle of cascading or tree multiplexing is very simple. Let us repeat again. Higher order multiplexers can be constructed using lower order multiplexers. Let us now consider the example of 8-to-1 multiplexer constructed using 2-to-1 multiplexer. Now, to obtain 8-to-1 multiplexer from 2-to-1 will require in all 7 multiplexers. Level 0 level 1 and level 2 multiplexers. All the multiplexers are of type 2 to 1 multiplexer. The level 0 multiplexers are considered to be the basic multiplexers which accepts all 8 data inputs, but 2 inputs per multiplexer. So, as you can see, first level multiplexer accepts 2 data inputs D0 and D1. The second multiplexer at the same level accepts D2 and D3. The third multiplexer will accept D4 and D5, and the fourth multiplexer will accept D6 and D7, and all of them are connected to common select line, that is S0. Naturally, these all 4 multiplexers will decide whether the first or second input is to be transmitted to the next level multiplexer. The second level multiplexer will act like 4 to 1 multiplexer. So, obviously, we are combining two 4 to 1 multiplexers together, and the output of two 4 to 1 multiplexers are once again multiplexed to get 8 to 1 multiplexer. Look at the second level multiplexer. The select lines, those are connected over here, are S1, whereas the last multiplexer level contains S2. So, the last multiplexer input is 0, which indicates one of 4 inputs will be allowed to transfer to the output, and when S2 is 1, it transfers lower 4 to 1 multiplexer output to the final 8 to 1 multiplexer output. This is the way we can construct 8 to 1 multiplexer. Let us construct similar 8 to 1 multiplexer using 4 to 1 multiplexer. The block diagram contains 2 4 to 1 multiplexers and 1 2 to 1 multiplexer. The MSB of the input select line is connected to the higher level multiplexer, and the lower level multiplexer receives S1 and S0. So, as it is seen from the function table, when S2 is 0, the first 4 to 1 multiplexer will send any one of the input to the final output, whereas when S2 is 1, the second multiplexer will transfer the data from D4 to D7 to the final output. So, the function table is self-explanatory. Let us consider the applications of multiplexers. There are many applications of the multiplexers. So, for example, we can use multiplexer for data routing. We can use it for forming the data bus for microprocessor or microcontroller. We can use multiplexer as a switch setting comparator. Multiplexer has a popular application as a function generator. We can convert parallel data to serial one. Cable TV signal distribution is a popular example. Almost all telephone networks prefer to have multiplexers and demultiplexers, and sharing of printer or resources is a common example in computer networking. Multiplexer can be used to route digital data under the control of data select lines. To display the content of one of the two BCD counters on a common 7 segment display is one of the important application. When S is equal to 0, multiplexer should select first data source. When S is equal to 0, the counter 1 data will pass through 2 to 1 multiplexer given to decoder driver, and the binary input of this counter will be displayed on 7 segment display. In this case, the counter 1 contains decimal 5, it will be displayed on 7 segment display. Let us now study another case when S is equal to 1. When S is equal to 1, the multiplexer should select second source. Let us see. When S is equal to 1, the counter 2 contains decimal number 2. Now, this number 2 will be passed through 2 to 1 multiplexer given to decoder driver, and 7 segment display will provide a digital display of 2. Multiplexers can be used to construct a data bus structure for microprocessors and microcontrollers. In this case, multiplexers are used in such a manner that it accepts data from various multiple bit sources, for example, registers, and connects the desired source to a data bus under the control of select inputs. Let us now consider the construction of this data busing structure. We are considering 4 registers, namely A, B, C and D. Each one of them is providing 4 bit output, which are labeled as A0, A1, A2, A3. The same thing is true for B, B0, B1, B2, B3 and so on. To get bus structure, we must use dual 4 to 1 multiplexer for all these applications. Let us consider 2 dual 4 to 1 multiplexer and their interconnections are shown here. Now, the select lines S0 and S1 will select any one of these registers at the output, but note that while making the interconnection, the LSB of the first register will go to the first 4 to 1 multiplexer, LSB of B, LSB of C and LSB of D is given to one of the 4 multiplexers. Similarly, the other bits are connected to the next 4 to 1 multiplexer and so on. So, this is the way how do we interconnect. When S1 and S0 both are at 0 0, then register A contents will appear on the data bus. When S1 and S0 is equal to 0 1, then register B contents will appear on the data bus. When S1 S0 is equal to 1 0, then register C contents will appear on the data bus. Similarly, when S1 and S0 is equal to 1 1, the register D contents will appear on the data bus. Another application of multiplexer is switch setting comparator. A 3-bit code is used to represent one of 8 possible switch positions, and an output signal is generated to indicate equality. The figure indicates the use of 8 to 1 multiplexer as a switch setting comparator. When the input code is 0 0 0, then the mux output is 0, thus the lamp is off. Let us consider another code. When the code is 0 0 1, the multiplexer output is still 0, thus the lamp is off. When the input code is 1 0 0, then the multiplexer output is 1, thus the lamp is on. This simply indicates your data input D4 is connected to VCC. Naturally, the input code matches with the switch position. Thus, we have a switch setting comparator. When the input code is 1 1 1, the multiplexer output is 0, thereby keeping the lamp off. This indicates any incorrect code will keep the lamp off, and when the input code matches with the switch setting, then the lamp is on. Let us consider another application of multiplexer, multiplexer as a function generator. Let us understand the procedure of using multiplexer as a function generator. The procedure is very simple. First, let us write the function in sum of product form. Based on this, let us identify the required multiplexer. Step number 2, let us assign the appropriate input line to each product term. Use the decimal number corresponding to each term in the expression. Step 3, connect these input lines to logic 1, that is VCC, and step 4, all other inputs are connected to logic 0, that is ground. And last step, apply the inputs to the select lines of the multiplexer, thereby producing the desired function. Let us consider the implementation of some given function. Let us say function f is equal to a bar b bar c or with a bar b c or a b bar c. This simply indicates we can have sum of minterms 1, 3 and 5. Now, the Boolean expression is clearly given. This indicates there are only 3 terms, those are present. These are representing, we have the data input D1, then D3 and D5 are to be connected to logic 1, and rest of the data inputs are connected to logic 0. By applying proper select lines, that is ABC input, we will get the desired output function. Let us consider another example of implementation of full adder using multiplexer. Multiplexer can be used for generating any desired truth table. We can see from the truth table, if you have A, B, C as the inputs of full adder, the possible combination will give you the desired sum and carry. In this case, we are just focusing on sum. Wherever the sum term is 1, those outputs are to be implemented. So, the multiplexer output is similar to the sum output of the full adder. From the truth table, we can connect wherever the sum is 1, those inputs are connected to logic 1 and rest of the inputs are connected to logic 0. By applying the corresponding ABC inputs, we can definitely generate the necessary sum term. So, sum term is expressed in terms of sum of minterms 1, 2, 4 and 7. Demultiplexer has a single input and n output lines. Demultiplexer can be visualized as reverse of multi-position switch. The select lines permit input data from single line to be switched to any one of many output lines. Demultiplex means one into many. A demultiplexer reverses the multiplexing action. In other words, the demultiplexer takes one data input source and selectively distributes it to one of n output channels, just like multi-position switch. It also has m select lines for selecting the desired output for the input data. This demultiplexer is also referred as data distributor. The mathematical relation between select lines and the output are 2 raised to m is equal to n outputs. The basic relationship between the select lines and number of outputs indicates we can have different types of demultiplexers. When m is equal to 1, we have the first simplest demultiplexer. One select line allows the input line to be distributed to 2 outputs. It is 1 to 2 demultiplexer. Similarly, when the number of select lines are 2, we have 1 to 4 demultiplexer. The input is D The select lines are S1 and S0 and the outputs are 4. We can label them as Y0, Y1, Y2 and Y3. Similarly, when we move on to the higher order demultiplexer, we have m is equal to 3, wherein we can have possible 8 outputs. So, these 3 select lines can allow the input to be distributed amongst the 8 output lines, either by in a time division multiplex mode or frequency division multiplex mode. Similarly, when m is equal to 4, we have 1 to 16 demultiplexer, and 4 select lines can redistribute the input data amongst 1 out of 16 different lines. Let us study 1 to 2 demultiplexer in details. The symbol of 1 to 2 demultiplexer is shown here. 1 to 2 demultiplexer accepts single data input D, one select line S0 and 2 outputs Y0 and Y1. If you look at the function table, it is very clear that the select line will decide whether the output is to be distributed to Y0 or Y1. So, when S0 is equal to 0, you can see Y0 carries the data D. When S0 is equal to 1, Y1 receives the input data. Let us now construct the logic diagram from function table. Y0 is equal to S0 bar D0 and Y1 is equal to S0 D2. It is very clear from function table, these two logic expressions can very easily be derived. Now, as you can see, both the outputs carries D as the input and other select line could be either in complemented or uncomplemented form. Let us now consider the example of 1 to 4 demultiplexer. 1 to 4 demultiplexer as usual has a single data input, but there are 2 select lines, thereby we can get 4 outputs. These outputs are Y0, Y1, Y2 and Y3. Depending upon the inputs, the output Y would be selected. So, for example, when S1 and S0 both are 0, 0, Y0 will receive the data input. When S1 and S0 is equal to 0, 1, Y1 will be activated and will receive the data D. In case of third case, when the select inputs are 1, 0, Y2 will be selected and will receive the input data D, and in the last case when both the inputs are 1, 1, the output Y3 is activated and receives the data D. Let us now consider the logic symbol as well as the logic diagram for 1 to 4 demultiplexer. We can obviously derive the logic diagram from the function table. As you can see, there are 4 outputs. Let us write the Boolean expression for each output. Y0 is a product of 3 terms. So, naturally we have to use 4 AND gates. 2 select lines can be complemented or uncomplemented form. Naturally will require 2 inverters or NOT gates. We can apply the common data input to all 4 AND gates. The other 2 inputs would be dependent upon the corresponding output. As it is seen from the function table, first output can be obtained only when S1 bar and S0 bar are active. Similarly, the output Y1 is enabled when S1 bar and S0 is active, whereas Y2 is enabled when S1 and S0 bar is active, and Y3 is enabled only when both S1 and S0 are active. Now, we can definitely generate the similar higher order demultiplexers like 1 to 8 or 1 to 16 demultiplexers. Let us now study the TTL demultiplexers available commercially in the MSI IC form. IC 74138 is 1 to 8 demultiplexer. The outputs of this demultiplexer are inverted. IC 74139 is a dual 1 to 4 demultiplexer and which has inverted output. IC 74155 contains dual 1 to 4 demultiplexer, but with a complementary inputs. IC 74156 is also a dual 1 to 4 demultiplexer. The only speciality of this is the outputs are open collector. So, naturally we need to have the corresponding open collector circuits. IC 74154 is 1 to 16 demultiplexer, the outputs are same as input, and the last demultiplex IC under TTL family is IC 74159, which is also a 1 to 16 demultiplexer. The outputs are same as input, but the outputs are open collector. Demultiplexers can also be used in many applications. Let us study the applications of demultiplexer. Here we will just label the applications. Demultiplexer can be used for demultiplexing the data. It is also possible to distribute the clock to many sources. In addition to that, demultiplexer as well as decoder can also be used in addressing the memory. There are several applications like stepper motor generator or stepper motor sequence generator circuit, wherein we require 4 phase clock. This could be very easily generated using demultiplexer. Just like multiplexer, demultiplexer can also be used as a function generator. Another interesting application that we can have is switch encoding, where you can encode the incoming data into a binary form. And one of the interesting example is serial to parallel converter. We can accept the data serially and convert it back to parallel one. Let us now summarize the things that we have studied so far. A multiplexer is a combinational logic circuit which routes the data from many inputs to single output and are available in 2 to 1, 4 to 1, 8 to 1 and 16 to 1 forms. The multiplexer has 2m input lines, m select lines and a single output. There are many applications of the demultiplexers. Some of them are listed here. The more popular applications we did not discuss it are parallel to serial converter, cable TV signal distribution, telephone network as well as sharing the printer and resources. A multiplexer is a universal logic circuit because it can generate any truth table. A demultiplexer is a logic circuit which takes the data from one input line and distributes them to one of many output lines under the control of data select lines. Demultiplexer can also be used as a decoder. Demultiplexers are commonly used in following applications, which we have listed here. Thank you.